For this video, we're going to look at the Nobel Prize in Physiology or Medicine. The year is 1914. The person it is awarded to is Robert Bárány. I hope I pronounce it correct. For his work on the physiology and pathology of the vestibular apparatus. Here you see his Nobel Prize diploma. And here you see a patient with a condition called optokinetic nystagmus. We will see what it is later, but you can see that the eye is moving from the left to the right continuously. Then why he got the prize? Going from the official Nobel Prize site, the inner parts of the ear play an important role in helping us maintain balance. Irritation of the inner ear causes vertigo and spasmodic eye movements. Nystagmus, we already saw that. Bárány discovered that nystagmus occurred in one direction when he syringed a patient's ear with cold water and in the opposite direction when he injected warm water. The explanation was that changes in temperature made the fluid in the inner ear canal rise and fall, respectively. The discovery had a major impact on the treatment of diseases of the inner ear. As said, coming from the official prize, this is the link site. This is the link. Then some biographical information also coming from the site, summarized by me. He followed up the theories of Florence, Pequeña, Mach, Breuer and others and clarified the physiology and pathology of human vestibular apparatus. He had been attached to the Austrian army as a civilian surgeon and had tended soldiers with head injuries, which fact had enabled him to continue his neurological studies on the correlation of the vestibular apparatus, the cerebellum, and the muscular apparatus. During the latter part of his life, Bárány studied the causes of muscular rheumatism and continued working on a book dealing with the subject, even after he had suffered a stroke and was partially paralyzed. As said, this is from the biographical information. This is the wrong link. I will correct that. So that's done. And if you follow this link, you can read the complete biographical information. Here you see the inner ear with three canals, semicircular canals, which three dimensions, of course, can measure movement in the three possible dimensions, one for each dimension. Then the award ceremony is preached by Professor G. Holmgren, or rather the press release, because in 1914 there was no ceremony due to the First World War, which also resulted in the circumstances that the Nobel Prize lecture by Bárány was only given a few years later. I believe it was in 1916. Okay, the press release then. Florence had already proved by experiment that by stimulating the semicircular canals of the inner ear, certain rhythmical eye movement called nystagmus could be caused, and Pequeña showed that in human beings vertigo was induced by rotation. Meniere was the first to prove that diseases of the inner ear can produce giddiness. Later, a number of physiologists, especially Breuer and Ewald, studied the physiology of the inner ear. Otologists also made daily observation in this field, without, however, appreciating their significance and adapting them to the service of otology. After Bárány, in May 1905, had communicated his observation on catalytic nystagmus, there followed during the next 10 years a tremendous, almost revolutionary development of otology, in which Bárány's work was both the foundation and the central theme. Many other research workers also contributed, in particular Alexander, Neumann, Rutten and others. The starting point for a long time, otologists had been aware that the syringing of a patient's ear often causes dizziness. Some doctors had even observed nystagmus, but it was not known by what agency this came about or which organ released the phenomenon. Bárány found that syringing of the ear regularly produced nystagmus of a certain type. This nystagmus was connected with a feeling of giddiness. A patient whose ears he was syringing said to him one day that he experienced a strong sensation of vertigo when the syringing water was too cold. Bárány then used a very warm fluid in the syringe and the patient again complained of severe vertigo. Bárány noted the appearance of nystagmus here too, but the direction was the exact opposite to the one previously observed. The explanation was now clear. The decisive factor was the temperature of the syringing fluid. The so-called caloric reaction proceeded from the semicircular canals, in which the endolymph increases in specific gravity with cooling, showing a tendency to sink, whereas with warming, the specific gravity decreases and the fluid shows a tendency to rise. The flux or tendency to flux, which then appears in the endolymph of the semicircular canals, produces the reaction. It then followed that a series of earlier hypotheses could be ruled out. The essential facts are simply whether the labyrinth is cooled or warmed and what the position of the head is when the process takes place. The caloric reaction for the first time provided otology with a method of investigation of the excitability of the vestibular apparatus, which can be used in practically all cases. If the reaction is positive, then the canals are excitable, not totally destroyed. If it is negative, then they are destroyed, with a few easily checked exceptions. This very simple obtained reaction had become basic for our understanding of, and therefore for our therapeutic handling of, a number of labyrinth diseases, in particular those of an inflammatory nature. The mortality rate in a group of these, which used to be reckoned at 30 to 50%, has now been reduced to a minimum, according to some statistics, to almost zero. And this is mainly thanks to the caloric reaction and the labyrinth surgical method which have been there based upon it. Bárány also studied systematically the other vestibular reactions. He provided an example for the vestibular phenomena occurring after rotation, which was in sharp contrast to what had been thought before, and established the clinical and physiological importance of the so-called rotary reaction. By means of the so-called fistula test, he made a pneumatic hammer of the physiologist Ewald available for clinical use, and he gave the galvanic reaction the secondary place which it now occupies. He also studied the remaining phenomena of the vestibular syndrome and systemized them. He was chiefly concerned with developing the question of the so-called vestibular reaction movements. First of all, he established that vestibular disturbances of equilibrium occur in a regular manner in a certain relationship to the existing nystagmus, so that the change of position or tendency to change of position always occurs in the same plane, but in an opposite direction to the existing nystagmus. From this followed the interesting and clinically extraordinarily important fact that existing vestibular imbalance changes direction with an alteration in the head position. These imbalances, which may stem from the muscular apparatus of the trunk, corresponding with other analogous phenomena in all other muscles which are directed by the will. It can now be shown how each extremity or part of an extremity deviates from a certain position or tends to deviate in the same plane but in an opposite direction to the nystagmus caused or already present. This previously quite unknown phenomenon has become, through Bárány, so-called pointing test, an integral part of the examination method of ear and nerve specialists. It drew Bárány to important investigations into the function of the cerebellum. Bárány thinks that constant impulses are going out from the cortex of the cerebellum to all the muscles controlled by the will, which are thus held in a constant and, under normal circumstances, uniform state of tension, tonus. This tonus is influenced by the stimulation of the vestibular apparatus in the regular manner already indicated. If one applies the simple test, Bárány's so-called pointing test, of raising the outstretched arm from a downward position upwards, opposite a suitable situated fixed object, like a graduated disc, boavie, it will be found that with repeated attempts, every normal individual reaches approximately the same spot each time with the eyes open or closed eyes. If the same test is repeated after stimulation of the vestibular apparatus, thus after syringing an ear with cold or warm water, The subject will pointedly wrong with closed eyes and always in the same way, that is to say, in the same plane in which the nystagmus occurs, but in an opposite direction. The direction will be the same, mutatis mutandis, if the arm is moved in a horizontal plane or if the test is made with the leg, forearm, lower leg, trunk, head, etc. Let us imagine a horse walking and being led by two stretched reins. The horse can be led out of its direct path either by a stronger pull or one rein or by loosening or the other. In Bárány's pointing test, the cortex of the cerebrum represents the active force, the horse, while the cerebellum cortex lies the tonus. One must assume it has a center for the tonus which is directed against the sagittal axis of the body, inwards, and also a center for the tonus away from this axis, thus outwards. When the arm is directed into the horizontal plane, one must assume, as regards tonus, it is being influenced by one center for tonus in an upward direction and for one for tonus in the downward direction. Consequently, one must assume for each point in the body the presence of four tonus centers in the cerebellar context, one for each of the four possible movement directions. By closely study of cases of isolated damage to the cerebellar cortex and by suitable development and adaptation of the Trendelenburg method, by which the cortical center can be temporarily paralyzed by freezing, Bárány also succeeded in establishing the pressure, presence and position of some of these centers and thereby inaugurating a kind of topical cerebellar diagnostics of a very promising nature. After the outbreak of war, Bárány's efforts were partly directed into other channels, in almost all cases where projectiles had penetrated into the brain, taking with them infected particles of skin and clothing. Infection occurred which sooner or later led to death. Bárány assumed that the so-called open method of treating wounds generally current at the time was directly favorable to this infection and attempted in suitable cases, after careful cleansing of the cavity, to close the wound with a primary suture, thereby preventing continuing infection from the outside. With this method of treatment, he obtained a considerable and obvious improvement in his results. Okay, that was it, the summary of the press release. As you want to read the complete press release, you can follow this link here to the official Nobel Prize site. Here again you see the semicircular canals. Only one, the one that detects horizontal movements, the other are for movements in the other directions. As you can see, if the head moves to right, the fluid in the canals stays behind. This is inertia, so in relation to the outside of the canals which moves with the head, the water moves to the left in both canals. On the left side you get inhibition, and on the right side you get excitation, and the brain thus concludes that the head is moving to the right. That's how it works. Push-pull is that called. And here you see something else. Here you can see also when there's a movement. Here you see the circle, and the movement is in this direction. As you can see, the fluid in the canals tends to stay behind. This is also given through via the brain to the eyes, which react with a compensating eye movement, as you can see. Yeah, okay. That was it for the moment. Next week we will go into his Nobel Prize lecture, which was just not given in 1914, but a few years later. But nevertheless, we will deal with it. For now, thank you for watching, and maybe till another time.